Howdy crew! In this video we're going to discuss center of mass of laminar surfaces. Sounds like a complex skill, but it turns out to be just another one of those applications of anti-differentiation and integrals. So what we're going to do is we're going to discuss what a laminar surface is, what a center of mass is. You probably have a pretty good idea of what a center of mass means, but we want to make that as formal as possible. And we're going to apply that understanding to both rectangular surfaces and non-rectangular surfaces before I show you some examples. So here's what a center of mass is. Center of mass is the point at which a surface will balance. So think about this picture over here on the right with a spinning basketball on the tip of your finger. The center of mass is this red point in the center of that ball directly above the point where it's balancing. Now a laminar surface, or a lamina, is a surface that's so thin that we think of it as being two-dimensional. Think about a sheet of paper, a piece of sheet metal, a piece of cardboard, something that is very thin, and we consider it to be two-dimensional, even though we know that it's three-dimensional. What we're also going to assume today is that that surface is made of the same material, so it has the same density all the time. That will simplify things for us. Now our goal is to find the center of mass of any region that I give you. And we're going to show you how to do that. First things first, we're going to find the center of mass of this lamina. If you notice in this picture, I give you the surface area, but I don't give you any details about the thickness. Remember about the thickness of this? We're assuming that that lamina is so thin that we can think of it as two-dimensional. So the material that it's made of and how thick that material is really doesn't do much for us. But I've got that picture for you, and we know that the center of mass of any rectangle is just the middle of both dimensions. So if you notice, that blue lamina is broken up into two different rectangles, the big one on the left and the small one on the right. Should be pretty clear to you that the center of mass of any rectangle is just going to be the middle point, the middle in both the x direction and the y direction. What I am going to do, just to simplify things, is I'm going to draw an x-axis and a y-axis on this picture so we know what we're dealing with. Should be pretty clear that that red dot is going to be the center of mass of the first rectangle, and this blue dot will be the center of mass of the second one. And you'd agree with me that the center of mass of the whole thing should be somewhere in the middle of the two. And we're going to find where that spot is. Now we do have formulas for both of these. This x bar, x with that line on top of it, well, how do we find the center of mass in the x direction? And what we're going to do, there's the sigma, so we're going to end up adding stuff up. So what are we really going to add? We're going to find the sum of the x coordinates. So notice however many of these rectangles that we have, we're going to add up whatever the x coordinates are times the corresponding area of the rectangle. So what we're going to need is we're going to need the coordinates of these 2 points. So in this case, this distance in that first rectangle is 4, half of it's 2. In the y direction, I have 6, so halfway is 3. And in the other one, we may as well do that. Half of 2 is 1, and I need to add in my 4 from the first rectangle, so my x coordinate is 5. And in the y direction, I got to go up 2. The whole thing is 6. I'm going to take away the 2 that we see here, so this distance is really 4. Half of it's 2. 2 and 2 makes 4. Okay, so what are we really trying to find here on the top? On the top, this x bar is the sum of the x coordinates times the corresponding area. This x is the x coordinate. This a sub I is the area of the rectangle. So what does that look like in the first one? Well, for the x coordinate of the first one is 2 times the area of the first rectangle. Well, that's just 4 times 6, which is 24. And I'm going to add that to the x-coordinate of the second rectangle, that's 5, times the area of the second one, that's 8. Now on the bottom of this fraction, I have the sum of all the areas, or in other words, the total area of the whole thing. And that should be pretty easy to find. That's just 24 plus 8. Just the area of both blue regions. Now when I do all that adding, all of that multiplying, I get a total of 11 over 4, or 2.75. Okay, I'm going to leave that there for now. On the y side, this y bar, we're going to follow the same process. I'm going to take the sum of the y coordinates times the area of the corresponding rectangle. So for the first rectangle, my y coordinate is 3, times the area of that rectangle, 24, plus the y coordinate of the second one, that's 4, times its area, 8. And again, on the bottom is just going to be the total area, 24 plus 8. When I go through and find that total, that turns out to be 13 over 4, or 3.25. So what do those two numbers mean? Well, the center of mass is just going to be x bar comma y bar. Or in other words, the point 2.75, 3.25, that's going to be that balance point, where if you stuck your finger directly underneath that point, this entire blue box would balance. So let's try to find that spot, or at least approximate it. So if this is 4, this whole thing is 4, half of it would be 2, 2.75 would be somewhere about here. And I would need to go up 3.25. So here's 3.25. So that starred point would be the center of mass. And like we thought of before, it's going to be somewhere in the middle of those 2 points. Now the question becomes, well, what about a laminar surface that looks like this, that's bounded by a curve? Now we've seen this picture quite a bit, but we want to make sure we understand how we're going to create a formula to figure this out. Now our basic understanding is going to be the same. To find this x bar, we need to find the sum of the x coordinates times the corresponding area of the rectangle. Now what you've noticed here is I have drawn this rectangle for us, that general rectangle. We want to make sure we label it. Of course, we know that our delta x is going to be on the bottom. That's the width of the rectangle. What's the height of the rectangle? Well, that's just f of x, whatever the function is. Now, I'm going to also draw in this middle point, that center of mass, the center of mass of just that rectangle. We know that that's just going to be the center of the rectangle. Now, our job is to figure out what this coordinate actually is. So on the x side, this spot is literally just x. However far it is away from the y-axis, that's x. So my delta x, or my x bar, is going to be just x on the top, times the corresponding area. Well, what's the area of this blue rectangle? Well, that's literally just going to be f of x times delta x, whatever that turned out to be. Now, how does an integral come into play? Well, we want to take a look here that our formula says we're going to need a sum. Now, what we've been learning over the last unit or so is anytime that we're adding up a bunch of these rectangles, what we're really doing is finding the integral over some bound. So our integral from a to b of that piece. Now, of course, we're not going to have delta x. We're going to call it dx instead. That's going to be the top. Now, on the bottom is just going to be the total area. And we know that the total area underneath a curve is literally just the integral from a to b of the function. So if I can find both of those integrals and divide the two, I get x bar. Now something slightly different is going to happen for y bar. Let's take a look what that is. I need to figure out what the y coordinate is of this red spot inside of our function, or inside of our rectangle. Now the question should be, how tall is it from the x-axis to that red dot? And you might be thinking, well, it's just half. It's halfway, which makes sense. It's half of the function, whatever it turns out to be. Now, times the corresponding area. What's the area of a rectangle? The entire function times delta x. Now again, we're taking a sum of it. So since we're taking a sum, that's going to be an integral over some bound from a to b. Now again, on the bottom, we're going to have our total area. The total area we know is the integral from a to b of the function. And we'll clean it up. We won't have a delta x. We'll have a dx instead. Now I do want to do some cleaning of this as well. If you want to take out the 1/2 out of the integral, you can. I'm going to leave it in, because sometimes it is helpful to leave it in. But I can combine here. The function times the function is just the function squared. All over the integral from a to b of the function dx. Now, how are we actually going to use this? Let's go do it. Find the center of mass of the lamina bounded by the square root of x, the x-axis, and x equals 4. So it's that blue area. I'm going to draw in the general rectangle. Always want to draw in the rectangle so I can get an idea of what's going on. Got my delta x. I know this is going to be the square root of x. Now we'll find x bar. X bar says I need the integral from 0 to 4. Those are my bounds, 0 to 4, of x. And why is it x? Because I need the x coordinate, that's this red line, times the function, square root of x dx, over the entire area. Now the entire area is the integral from 0 to 4 of just the square root of x dx. Now, how do you actually go about evaluating those integrals? That's something we've been doing for a while. I would recommend when you get to this point to separate your two integrals and solve them separately. So I'll start with the top first. So I'm going to find the integral from 0 to 4, x times the square root of x, well that's x to the 3/2 dx. I can integrate it. That's going to be bump up my power by 1 and divide by that power from 0 to 4. And when you do that evaluating, you end up getting 64 over 5. Now on the bottom, we're going to have the integral from 0 to 4 of just x to the 1/2 dx. Do your integrating, bump up the power, divide by that power, which turns out to be 16 over 3. What am I going to do with those numbers? It's just a matter of dividing by them. Dividing those two fractions, 64 over 5, all over 16 over 3, which turns out to be 12 over 5. So from there, that's your x bar. How do I find y bar? Well, again, that's going to be the integral over our bound 0 to 4. Now this time the y value is going to be half of that square root of x. So 1/2 square root of x squared dx. The reason why it's squared, 1, our formula says so, and 2, I have the area with the square root of x. I definitely want to clean this up a little bit. This is one where the 1/2 coming out front will make our lives a little easier. Square root of x squared is just x. And now I'm ready to integrate. Integration should be pretty easy here. Bump up the power, divide by that power. And when you do that calculation all the way through, you get an area of 4. Now, how am I actually going to get my y bar? We're going to take that 4 and divide it by the total area. Now, conveniently, the total area that we found was back here. So all I have to do is divide by my 16/3 to get my final y bar of 3/4. So again, let's make sense of what that really is. What this really is the point 12/5 or 2.4 and 3/4 or 0.75. That point, so 2.4 about right there and 0.75, about where that star is, that is the center of mass. Meaning if I had that surface laid out with some material and I put my finger underneath that point, it would be perfectly balanced. So let's summarize what we've done so far. We're going to find the center of mass using these 2 derived formulas. Now these are formulas that you're going to have to either know by heart or you're going to have to work through it using a picture like this one. If you have these formulas, you'll be in good shape. By drawing the picture, you'll be able to derive both of these formulas without a problem. Nice job.